Yes, so we have 3 talks in the next section, and we're going to start with Alfredo Kalaitzis. So let me introduce Alfredo. So Alfredo Kalaitzis, or Freddie as he wants, what he prefers to call him, is a hybrid applied research scientist, research engineer in the AI for Good lab of Element AI in London, working on applications that enable NGOs and nonprofits. His research interests lie in computer vision for satellite imagery, probabilistic modeling, and AI for social good. And today he's going to be talking about multi-frame super resolution by recursive fusion, HighRes-net, the tech, and beyond. Thank you, Freddie, for being with us. Now to you.
Hi, everyone. Thanks for the intro, Mauricio, and good to see you again, Magnus. Thanks for inviting me to this conference. Let me just share my slides really quickly. All right, can you all see this slide?
It's a bit blurry.
Yeah, okay.
Yeah.
We're going to super resolve that a little bit. Okay.
Yeah, no, it's fine.
So basically, this is the gist of the talk, right? But I promise you, this is the only gimmick. Everything from now on is actual machine learning. So this is work that I, sorry about these Zoom pop-ups. This is some work that I did when I was part of Element AI. I've actually left Element AI back in April, and now I've joined the Frontier Development Lab, which time permitting, I will talk about at the end of the talk, which is a NASA-funded initiative for accelerated science that uses AI for space science problems, earth science, and astrophysics, and so on. But here I want to talk about super resolution. So this is work that I did when I was part of the AI for Good lab, as Mauricio mentioned. And this was a joint work with Yoshua Benju's Mila, part of the Mila lab, a small part of it, that cared about environmental monitoring from space for both environment, but also for human rights. So this is what motivated, this application motivated this whole talk. And most of you have probably seen some version of super resolution in popular culture, either through Blade Runner or some CSI show. There was always this cliche of enhancing, or in MacGyver, where you can enhance infinitely on any image, on any video. Basically, you can create information from nothing, and you can like enhance to the point where you can see the tattoo on the wrist of some robber or whatnot. And this is very much a trope in sci-fi. But back in the real world, this is what super resolution actually looks like. So you've got some high resolution image. It can be a cartoon, it can be an actual photo. And what you do is you convert that into a low resolution version. So you downscale it. And you do this a bunch of times for many different images. And you create the kind of data set. So this is your typical learning to super resolve story. This is how they create these data sets. And then you learn a mapping from the low res back into the high res. So you learn to reconstruct the high resolution. And this is known as single image super resolution. And actually the results are quite impressive. So if you're really interested about artistic applications, then the state of the art in single image super resolution is pretty good. Like for instance now, if I focus on the upper left corner over there, you can see how well-defined the edges, the boundaries of the trees have become compared to its low-res rendering. However, the devil with single image super resolution is in the details, right? So if you look at the hat of this character or their scarf, you notice that a lot of the important detail, a lot of the art has been lost in the downsampling. Like, for instance, this kind of snake-like coils have been are unrecognizable, or there used to be like a whole scene in the hat of like a kind of a parade there that has been lost. Can I ask someone kind of like to say from time to time, just to make sure that I'm still connected? Okay, great. Cool. So here's another one where also in synchronous super resolution based on GANs, in this particular case, also has, sometimes can be a little bit too creative, so you can create too much detail. This is also known as a hallucination, so this is a technical term. So why is this so hard? What's happening here, and why is this information lost forever? I think this is something that you learn when you take a signal processing class. Usually the first thing that you learn is there is a certain limit to the amount of frequency you can recover that is dependent on your sampling frequency. So if we take this natural chirp-like signal with a linearly accelerating frequency, and then we digitize it, so we take a relatively high resolution digital version of it, 1 kilohertz, we can see that we can retain its oscillations, right, all the way to the end. But now if we decimate it times 4, if we did 250 hertz, you can see that that by the end, we'll find this phenomenon that is called as aliasing. And aliasing basically looks like, what you see looks like a lower frequency than the actual frequency. So basically that particular part of the data, that frequency is masquerading as a lower frequency, when it's actually in detail in actuality comes from a higher frequency, from natural signal. So that's why it's called aliasing. And now with satellite data, we have the opportunity to use more than one signal. So for instance, we have low Earth satellites like Sentinel-2, Landsat, and PROBA-V stands for vegetation. Because they're in low orbit, they fly around the Earth many times a day. And their streams, the data streams, are in low resolution, but they take multiple snapshots a day. And this data is either cheap or free. So the idea here is that instead of relying on just one image in high resolution, why don't we take all these many images in low resolution? So what you see here on the right is an actual, just a strip from a larger photo in high resolution, which is high res in this case is 100 meters per pixel. And on the left side, you see a different camera on the same satellite. So this is an actual instrument. This is not synthetically downsampled. You see for the same strip, many different time points of the same area, but now from the low-res camera, but me taking it at different times. Now, what's nice about this is that all these things can be fused to give you back a super resolved reconstruction of all of these low-res captures together. And in this particular strip, what is nice is that I'm highlighting this particular strip because there's a road there, so there's like kind of a junction in these irrigations, and this is an important feature, right? So if you're interested in agriculture applications, then you want to recover, let's say, the road networks between these irrigations to say support remote farmers, or you want to find the boundaries between the farms to do a kind of a segmentation. But you can't really see that information in any of the low-res images. So all that road structure has disappeared, has been kind of aliased away. But after you reconstruct the super res version, then you can very clearly see the road, and then you can do other downstream prediction tasks like road recovery, classification, segmentation, object detection, and so on. So this would be like kind of like a means to an end in further downstream machine learning tasks. Great, awesome. Here's another example, one with something that's called pivot irrigation farming. So again, here you've got these massive structures. Again, this every pixel is 100 meters here. So these are very, very big structures. And from the low res, you can really see what the yield is. You can kind of say it's on or off. But then after construction, you get a much better feel of what the yield is. So agriculture monitoring here could really benefit from this. Another one will be to track the changes in the path of a stream, which might be important for telling what area is going to be inundated in case of floods, for disaster relief or mitigation. So the idea here is that we're starting with a bunch of low-res views. So this is to scale. And we want to fuse them into an output that is basically has 9 times the size. This is in this case. So it's 3 times the height, 3 times the width. So you get 9 times information in a way. And the HighRes-net is the name of the model, and I'm going to kind of break it down really quickly for you, how it's doing all this. So you've got, typically, as in any machine learning model, you've got an encoding part, and then you have a decoding part. And in the zoo of deep learning models, there's always this encoding part that is basically a bottleneck of information that is forcing the model to retain only a representation that is dimensionally reduced, but is semantically meaningful. And every view in the input is turned into some encoding of same size, but more channels. And then we fuse them. So I want to touch on fusion a little bit. So fusion here, depending on what your training is, it can mean different things if you're trained as a physicist or if you're trained in the culinary arts. But in this case, we mean that we just take all of these blocks and we fuse them into a single global low-res encoding. And then in the decoding part, we flesh it out. So we do something that's known as upsampling, both in the signal processing and computer vision literature. And then we combine the channels. So we collapse the channels of the SR encoding into the final output. And keep in mind this, all of this pipeline is done with one channel in mind. So every one of the low-res views is one single channel. In this case, is for those of you familiar with remote sensing, is the near infrared channel of these satellite images. So how are we doing this fusion? This is where the recursive part comes in. So we're learning this fusion operator that turns a pair of low-res encodings into one. I'm not going to explain the details. The details of how it's done are kind of trivial once you look at the PyTorch code. It's not so important. But what's the trick here is that we learn a single fusion operator that we apply in every pair. And we apply this recursively until we end up with a single global LR encoding. So, this might give you some flashbacks of what you learn in computer science. One of the first algorithms you learn is a sorting algorithm called merge sort. So this is very much has the same divide and conquer kind of thinking. And what's nice about this is that you can parallelize it. So I'm not really I'm gonna give you I'm gonna touch very briefly on how the fusion works. So basically you've got these 2 input low-res encodings, and what the fusion does, it can either do nothing. So basically it takes one of them and just propagates it all the way to the other end of the right, or it can fuse them. And this trick is one of the most popular tricks in computer vision, and this is basically the crux of models that are called ResNets. And the idea is that the model has the ability to propagate, to imitate the identity function, or it can do some meaningful transformation. But that depends on, it kind of decides whether you should do that or not. And the other benefit is that the do nothing stream gives the network a sort of a highway of to backprop the error signals so that it can learn more efficiently. And this highway idea has been really important in deep learning because otherwise we wouldn't be able to make it very deep. Deep learning suffers from having too many layers because basically this error information, the signal to noise ratio becomes too low if you have too many layers. So these kind of highways allow it to backprop the error all the way to the beginning and learn much faster. Thanks. So, okay, so I touched on recursive fusion, and there are some nice perks that come with that. One is that we can parallelize it, and the other one is that this fusion happens in low res. So there's a whole other works. What they've tried to do is that first they upsample the image to the desired target resolution, and then they do the fusions. But as you probably surmised, that takes a lot of memory. So this particular architecture allows us to do all this processing in the lower res space. The reason why this multi-frame super res idea works is because the input images don't quite align. So in this cartoon, I have obviously magnified the differences, but in practice, the differences are at the subpixel level. So if you take all these low res and then you look at in an image browser and you do right, left, you'll notice that there are relative shifts, but at the subpixel distances. And this is what makes the super resolution work. So there's this aspect of co-registration, which means figuring out what the relative shifts are in the input. And the way we do that is that we take all the inputs, we compute this green little block on the lower left, which is, we call it the low-res reference. And that's literally just the median of all the low-res inputs. And then we copy that in every input as an additional channel. So that, in a way, acts like an anchor, as a frame of reference for the model to know how does each input differ compared to the frame of reference. And we tried different ways of using reference frames. So I want to just quickly describe what the scoring was used for this architecture. So we've got the PNSR, so which is the so it's a very typical score that people use in image reconstruction. PSNR is defined like this. It's literally just the mean square error between the ground truth high-res image and your reconstruction, in this case, the super resolved image. And it's just like a pixel-based mean square error. You take the log of that and you negate it. And so that's the PNSNR is the green thing. And then we have a baseline, which is something that in the context of the competition, the ESA competition, they defined as literally just taking upsampling each individual low-res image by cubic upsampling or by linear, I don't remember, and then taking the average. So that's like a really dumb baseline that doesn't address the co-registration issue. And then the score, the final score, is just this ratio. So the lower the score, the better. And here's an ablation that we did. We tried doing this co-registration trick by, this is what we call implicit co-registration. So we just add this additional channel in every input. And we can either use the mean as a reference frame or we can use the median. And we see that obviously by this simple trick, we get this massive boost in performance. So it's quite surprising. I was even surprised that this worked, because somehow by giving the network, presenting this network with this frame of reference, it could manage to know how to fuse these images, how to shift them before doing any fusion. And at the end, you also, if you want to get an actual loss all the way to the end, you need to know how your output is shifted relative to the ground truth. So there we also do some other tricks, like we use something called ShiftNet to figure out what the relative shift is between our reconstruction and the ground truth. So this is delta x, delta y. And we figure that out. Then we use a shifting and interpolating kernel to shift the final output, and then we compute the loss. So this is also known as a registered loss. So this is the full pipeline. And these were our results in the leaderboard. How much time do I have left? I think
you don't have more time left, actually.
Yeah, okay.
But you can use 1 minute to wrap up.
Okay. So I just perhaps I want to touch on how we use all this. So connecting it all back to the work that we did in the AI for Good lab. What we cared is we cared about an application of Amnesty International. So Amnesty International was one of our partners, and one of the big campaigns that they're running is raising awareness of the genocide that's happening in Darfur, Sudan, in Western Sudan. In the last 15 years, the Sudanese government has been going around burning villages, unfortunately, the evidence that Amnesty has been collecting is very circumstantial. It's basically just sneaking out videos out of the country, and it's not that kind of systematic collection of evidence that you need to make a case in the International Criminal Court. So something that my former boss, Julian Kornebich, did before he joined Element is he did this pro bono project with Amnesty where he showed a proof of concept saying if we scrape images from Google Earth, then we can train a ResNet to be able to do classification of burned huts or not. So this is something that you can show that you can find evidence of atrocities from space. But as you can imagine, with Google Earth, for one, that's you only see a single snapshots. So it doesn't really allow you to do this kind of continual monitoring that you need for protecting human rights and building a case for an international criminal court. And also, it can you can run into all sorts of legal trouble because the images in Google are basically licensed by Maxar. So what we did here is, but Maxar images are really important because they are the most high resolution images that exist out there commercially, and it's this kind of high res that you need to spot the detail. So the hallmark of destruction here is a bunch of walls with no rooftops, and in order to see this, you need images in high resolution, but these are too expensive. Like to get one snapshot, the whole Darfur region, it's costs millions of dollars to download those images from Maxar. So you can imagine an NGO like Amnesty, obviously this is out of the question. We can't afford this, to do this on a regular basis, even if they want to do this quarterly. So the idea here is that we did this second phase of Decode Darfur as part of AI for Good team. And we showed that, okay, let's take these single individual frames of Sentinel-2, which are very low res images, like 10 meters per pixel. And then we try to do classification, and we see the classification is very, very moderate. So the F1 score is is very mediocre. But now GPDX.
Sorry, Freddie, we only have 2 minutes left.
Yes, and we have.
So you can wrap up, please.
Yes. So yeah, the gist is that with doing some kind of spatial fusion, we could improve the classification performance of destroyed huts. And we wrote an article here about this work. And yeah, I'll take any questions you have.
Thank you, Freddie. So maybe we can have a very quick question. Are there any questions for Freddie? I think there is one question by Andrew Bart, so I'm gonna read it here. Are there potential problems regarding multiple time points between which the world has changed? For example, have you examined the effects of including frames pre and post crop burning on your outputs?
Right, so you're saying that you can spot, I think if I interpret the question correctly, is that destruction can also be inferred by looking at differences between two images. And for super resolution, obviously this is going to be a problem if you have differences in this many lower frames. But for the destruction case, in this application, actually that can really improve the classification. If there's like a change point, if there's a massive difference between before and after destruction.
Okay, Alfredo, thank you. So I think